So thank you to everyone for joining us today for a Linux Foundation Decentralized Trust virtual meetup. Today we are going to discuss one of the newest labs at LFDT, the Nightstream lab. We have one of the lab maintainers here today, Sebastian. We'll be talking about how Nightstream is a provable Nightstream provable coroutines for containers and contracts. And with that, Sebastian, please let me unshare and then you can take it from there. And I see your screen now.
Do you see my screen?
Yeah, I see your screen now.
Okay, great. Okay, so with that, time to get started. So thanks everyone for joining. So today we're going to talk about Nightstream, which is a system for provable coroutines for containers and contracts. So this has applications broadly, not just in the blockchain space, but generally in the end goal of having containerized software and proving properties of your containers without necessarily having to share the entire container state, which might be private. So the main problem we're trying to solve is there have been many attempts at doing privacy, like especially in the blockchain space, but most don't get any traction. It's been 40 years or so of zk technology. There are many reasons for this. Now, a lot of it is performance, things that have been resolved over time. But I think there's another issue, which is that the developer experience and the UX is pretty demanding. You have to go download wallets, get tokens, learn some new DSL, set up Docker, set up some proof server. Once you've gone through all these steps, you're now finally a user, and you have to go through a whole other funnel to fall in love with that software and be convinced you want to ship this for production grade software. So it makes it a bit hard to fall in love with privacy tech. So a lot of this is because zk has historically been a desktop first experience. And a lot of the users are these days on mobile or web. And so you're already kind of limiting your target audience. So I'm going to take a bit of a different approach with this talk, which is that we're not going to go super deep into the cryptography. Rather, I want to share the overall design goals, what we're trying to build, why are we doing this? And hopefully with that, it'll give you much better context for some of the more technical slides later, but just generally to understand what is the purpose of Nightstream, why did we start this project at the LFDT? So the solution is, what if we want to build some kind of OS that has privacy preserving primitives? So if you had some kind of OS that ran in the browser, you would have multiple different things, right? You'd have some kind of node that's running maybe a blockchain or generating proofs of some computation. You might have some applications. Some of these might be like financial applications like Uniswap. Some of these might be regular applications, like maybe you're running some Game Boy game. And so we'd like all this to be able to run in some containerized environments where each application is its own container. So containers cannot talk to each other other than through the host. So this is just a visualization of a typical container setup, but just kind of as a more visual way to see it. So ideally, you want the node and the ledger, or anything you might have as like a blockchain node perspective to be able to run the browser, as well as you want the apps to be able to run the browser. You might need, if you're doing crypto stuff, to have wallets, or if you're doing government stuff, you probably need some kind of decentralized IDs. So have these run in the browser. You also need the proof system to be able to generate cryptographic proofs of the execution to run the browser. And then you might want these apps to be sandboxed so that they're properly containerized. They can't mess with other stuff on the user's machine. And you might want some of these applications to be provable. That's to say, you can actually generate proofs of the state of this. So I think a very easy to understand example is, imagine you're playing a game of Pokemon and you want to prove that you really did capture a monster and you did not game shark or cheat your way to that monster, but you really caught it through playing the actual game. But of course, like all containers, we want to be somewhat modular. So you can run stuff either in the container or out of the container. And obviously running in the container is easiest approach, but we want the ability to hoist stuff out of the container. Just like in Docker, you can have stuff talk to the outside world if you decide to do that. So to enable this, we needed to leverage a few key technologies. The first one is this concept of Wasm components. And if you're familiar with containerization, you've probably heard of this concept. So Wasm is not necessarily a new idea. It dates back to the last decade. And they were called Wasm modules. The problem with Wasm modules is that they're very much a black box. So you receive a bunch of different Wasm programs. Are these boxes compatible? It's hard to know. They're just different black boxes. Of course, if the host knows this is a specific program, they might know that these are compatible, but it requires, application-specific knowledge to know if you can combine these. A new system is called Wasm components, which allows you to ship Wasm modules with type definitions bundled into it. And then you talk to the Wasm modules over this Wasm interface type system. Now, the benefit of this is that now that you have a declared type interface, you can actually check if two systems are leveraging the same type. And if they're leveraging the same type, then it means that it's expected that you can pass data between them and have it work. So it makes it much easier to combine these together. And in fact, this has been quite pushed for in the container space. So for example, there's many different providers like Akamai that have invested a lot in these technologies. There's some projects like Wasm Cloud. Docker is based off the Open Container Initiative. And recently, the OCI format now allows Wasm modules natively. So you can actually upload Wasm modules directly to Docker Hub or all the other container registries. So just an example, how would you represent a command line application? Well, there are many standards that are called WASI, so WebAssembly System Interface. And of these many standards, for example, there's WASI-CLI, which allows applications to print the console or get CLI arguments and so on. So this allows you to specify what your application needs to operate. And based off this, you can build kind of a permission system where the host chooses to potentially provide an application with HTTP functionalities or kind of gatekeep these as required. So this application, like in this case, a Midnight Node, would not be printing the console. Rather, it requests the host permission to print, right? And the host is the one that grants that permission. So the key idea is that instead of, for example, an app making an HTTP request, the app requests the host to make the HTTP request on its behalf. So that means that the host could decide to block either HTTP requests entirely or block based off some specific URL or some specific parameter. The guest can do this over the WASI HTTP bindings. So it allows for some easy sandboxing of your applications, which is really awesome. So the key idea is we want everything, in the mockup we showed earlier to be a Wasm component. And so if everything's a component, it means that if we manage to build a proof system that can generate proofs of these components in some way, we're now able to have proofs of containers in general. So how do these components talk to each other? Well, fortunately, there's a tool for that called WRPC, which allows for you to do RPC over Wasm components. So for example, you can have different Wasm components all running their own WRPC instance. They're discoverable at different localhost URLs. And these RPCs are importantly automatically generated from the types. So you don't need to define your own protobuf schema or these other kind of concepts. Just from this web file, you already have to declare to define the interface between your components and the host. You automatically get an RPC for it as well. And so now you have components able to talk to each other over an RPC format. So for example, if you have a specific application and proof system, they could talk to each other over WRPC. So one of the great things about this is that it allows for piecewise offboarding that you get in a system like Docker. So a bad design would be that if you have a specific application, this container that you like to hoist out. So for example, you don't want your node to run inside this, Midnight OS. You want to run it on your local machine or in some other cloud provider. It'd be really bad if you have to leave the entire sandbox just to offboard a single component. But instead, we want to allow this optionality where you can hoist out specific components. And the way that would work is you kind of scratch off the local host URL for WRPC, instead have the WRPC connect to some other host, Azure, Google Cloud, or so on. So by leveraging WRPC for cross-app communication, it gives us this easy way to hoist things out to separate locations, but do it in a way that does not break this kind of containerization system we have. So this allows for a much better funnel, which is like the bad funnel would be you use Midnight OS, you do cool stuff, you run into a single issue, now you have to offboard entirely to some desktop experience. The better funnel is that you have to, potentially progressively offboard one by one as you potentially hit the limits of what you can do in the browser. So there's still some problem with this, which is how do we render UI in a safe way? Like if you're using Docker, usually there is no UI component, so to speak. But we want UIs especially for our specific use case. The problem is, of course, running arbitrary JavaScript on the host is not safe because the JavaScript could muck around and cause a lot of damage. And sandboxing the entire JavaScript runtime is very expensive because now you have to spin up a V8 instance possibly for every single container, which is just memory-wise not really feasible. So fortunately, there's a new technology that's been standardized last year called WebGPU that helps us. So the idea of WebGPU is that it allows the browser to access the GPU directly through this specific interface. So it allows for these applications not to be rendered through JavaScript directly, but be rendered through WebGPU instead. And notably, there's a project called WasmGFX, which allows you to have with file bindings for the for the WebGPU interface. So you can access WebGPU directly from inside the container. So for the typical app logic, you'd go through the with file you have, for CLI, for HTTP requests, and so on. And then you would pass in a different file, like with file into the host, from the host to the dApp, which says like you can access the graphics API, the GPU directly if you need access to it. And so one of the benefits of this WebGPU approach over other technologies like WebGL that have existed in the past is that WebGL is primarily for the graphics pipeline. So you have access to, fragment shaders, for example. But you don't have access to compute. You can't do compute shaders. WebGPU, on the other hand, not only has access to the graphics pipeline, but can also do compute shaders. So we kind of get a 2-for-1, which is that we can allow these containers to not only render their UI in a sandbox way, but we also allow these containers to access the GPU so we can leverage GPU acceleration, which is very important for cryptography because a lot of the cryptography we do is very heavy. And so we need every inch of performance we can get. So now that you have some idea of the overall goal, what we would like to build, of course, we have to think about what would be the ideal proving system. How can we really enable this in practice? So of course, we need to at least be able to prove Wasm execution given our model, especially the Wasm component model. But we have a few other requirements that are a bit tricky. So for example, you have to prove possibly infinite programs. This is a bit tricky because if you think about historic proof systems, they're primarily focused on proving one-shot execution. You prove a small thing, you generate the proof, and you move on. But for a lot of applications in container, they are running for potentially days, weeks, months, years. A lot of people, when they're setting up a container in some cloud service, they want to just deploy it and forget. We also need to generate a privacy-preserving proof. So we need to be able to prove statements about the container state without having to reveal the entire container. And we would like it to be able to run in the browser, which is very hard because the browsers are memory constrained. So we don't have as much resources as we would be able to have on desktop. So the goal of Nightstream, which is the original topic of this conversation, is how can we build a proof system that can enable this kind of experience? We think that's going to be an increasingly large demand for kind of trustless containers in the space in general, not just in finance, but across a bunch of different industries. And so the goal of Nightstream is to try and build a proof system that can handle this flow. So how do we actually do this in practice? Well, there's a few key decisions we made for this proof system that we think will enable us to achieve this. First off is how we prove instructions. So I'm saying, okay, you can prove execution for program, but how do I actually prove Wasm execution? Well, there's been some previous approaches to this. So for example, a lot of people previously handcrafted circuits for Wasm. They said, okay, if you're familiar with proof systems, a lot of them work kind of like electrical circuits. So you have to manually set up circuits together. And so they just sat down and opcode by opcode manually wrote circuits for each opcode. This is complex to author, hard to update, and it's also hard to pivot. If at some point you decide that you need something more than Wasm, you have to go through the same exercise for a whole new different opcode set. A lot of other projects just instead don't use Wasm at all, and rather create some specialized zk-specific opcode set that's easier to prove, and then build Wasm bindings around that. These can be very good, but the problem with specialized opcode sets is that, of course, it requires all the developers to specifically target your platform. They lose the kind of generalization that you get with something like Wasm, where a lot of programming languages can easily already target this environment. So what we've adopted is this concept called a lookup-centric architecture, which is a concept that's relatively new in the zk space. But the key idea is basically to represent every instruction as a table. So if you think about it, the add instruction is basically a table of all possible additions. If you add 0 to 0, you get 0 and a 0 carry, and so on. And so you build up this massive table. Now, of course, if you have 64-bit numbers, this table is absolutely massive in size. And so there's a lot of clever tricks and cryptography required to make this table not actually have to be physically instantiated in your memory. So you can just assume that this has been solved. This is like new cryptography from the past 2 or 3 years that have been trying to tackle doing this. And so fortunately, there's some papers on this topic. Probably the most well-known one at this point is called Twist and Shout, that talks about how you can instantiate these kinds of tables in a way that not only does not blow up your memory, but actually makes it zk provable. And so Nightstream is all set up to support a plugin API for your own tables. So the idea is you could have riscv or Wasm as generic instruction sets, or maybe instruction sets for blockchains like EVM or Plutus or Minokawa, which is a different LFDT project. Or perhaps different instruction sets entirely, like you want to have a Game Boy emulator or NES emulator. The idea is that all these instruction sets, you just represent them as tables of every possible opcode. And then you can combine all these down into some lookup table API, and then you can plug those into Nightstream. So instead of making our project Wasm specific, we want to be able to represent containers in potentially different environments. And of course, the ability to support these blockchain-specific languages also makes it great for any project that wants to use Nightstream for blockchain or ledger use cases. So if you think about this picture in the past, maybe my node is running in Wasm, maybe my Uniswap DEX is running in EVM, maybe I have this Game Boy emulator is running in this Game Boy opcode set called SM83. So we saw this tricky part, which is, as I alluded to in the past, some programs never end. So for example, this application, which is a decentralized exchange, usually only runs a few lines of code and then finishes. Your swap is only a few things. It's like, okay, get the user balance, the smart contract balance, check if the balances match up, if so, execute the swap, and then this smart contract finishes. So it's a fairly small program. However, some other programs are long running. So for example, if you're playing video game, you turn on your Nintendo, your PlayStation, your Xbox, and you just leave it running until you finish your game session. But you may need proofs of intermediate state. So for example, if you're playing a game, you might at some point catch a Pokemon and you want to trade that Pokemon somewhere else, and that person wants to check that you really did catch that Pokemon and you did not use Game Shark or any other cheating methods to cheat that Pokemon into your system. So you may need these proofs of intermediate state. Now, of course, these long-running programs are not exclusive to games. There are many applications that never end. Of course, a lot of servers never end, but also even on consumer hardware, for a lot of people, they have Slack running or Chrome running or their computer itself, the operating system running for oftentimes days, weeks, months on end. And so we want to be able to represent proofs of these possibly infinite programs, but still be able to prove intermediate state. So there have been some attempts at doing this in the past that partially solve the issue. One is, of course, like the very naive approach, which is that memory grows as runtime grows. So you don't bound the execution, but just the memory requirement goes up over time. This is doable in some specific use cases, but especially on consumer devices, especially mobile and browser, you hit the memory limits very fast. And so this is not really a feasible approach. A different technique is called recursive snarks, which has been one of the main ways to do this for the past decade, which is to combine full proofs together. So for example, you have proof of program A and a proof of program B, and you combine these together into a single proof of program A and B. The problem with the recursive snarks is that they combine full proofs together, whereas what we want is granularity at the opcode level, right? We want the ability to run a few instructions, pause, generate a proof, see if there's any intermediate state we need to prove. If not, we keep going, do the next part and do the next part. And so we need this granularity that typical zkVMs do not provide you. And so instead, we use this concept called folding schemes, which is relatively new in the past 3 years or so. And the idea is basically you take your program, you execute your program, you get a series of opcodes as your trace. So this is your program execution. At every step, you run some zk system to generate an instance of that opcode. And then you will what they call fold these different instances together based off some batch size. You see, for example, let me run 1,000 opcodes and then fold 1,000 opcodes. Then run the next 1,000, then fold again. And so you're basically combining these instances every set of opcodes and aggregating them into a running proof. Now, the benefits of this system is that you can easily constrain the number of steps based off your target max memory. So the idea is that you say, okay, for one fold instance, I'm allowed at maximum maybe for example, 500 megabytes. You say, okay, for my opcode set, maybe I'm running riscv, maybe 500 megabytes corresponds to 10,000 opcodes. Okay, so I'm going to pick my full step size to be 10,000 opcodes. That way I know that my proof system will never cross 500 megabytes, so I know I have upper bound on my memory, which is required for a lot of these constrained devices. And so this folding system gives us kind of what we want to be able to model these infinite running programs, because now you can have multiple infinite running programs in parallel, and you can keep generating intermediate step proofs at every folding boundary. And you can do so without one program blowing up the entire memory of your container. So fortunately, lattice-based cryptography actually can give us this. There's notably a paper called NEO that introduces folding for lattice-based cryptography. The benefit of lattice-based cryptography, as you might have heard, is that it's post-quantum. So actually, a lot of cryptography is currently being moved to lattices in preparation for any potential quantum adversary. So it's great that we are able to do this, not only to get these properties that we need, we also do it with a post-quantum scheme, which is increasingly a requirement from governments. A lot of governments will say, okay, if I am going to run my software and your container, it needs to have some guarantee that's secure against a post-quantum adversary. But not only that, it allows us to leverage linear algebra techniques in hardware acceleration that is currently being pushed a lot on the AI front. And so by having a proof system that also has some similarities with a lot of the math done for AI, we can kind of ride this wave of AI infrastructure and specialized hardware being generated. We still have one question, though, which is when do we fold? A lot of times these are picked as fixed step size. So a priori, you decide the step size. You say, okay, the step size will be 1,000. But you could also maybe do a heuristic. But this is not just a performance question. It also affects what intermediate states can be proven. Because as you know, we decide that, okay, you're proving statements on these folding boundaries. And so because of this, programs and developers may want to manually control when the folding step occurs, in a sense. So you want to have the control flow enshrined in the language. And so to enable this, as part of the LFDT Nightstream project, we have a language called Starstream, which is based off this concept of algebraic effects, which allows this kind of control flow. Notably, this kind of folding is a specific way of implementing a technique called IVC, which is incrementally verifiable computation. So we want IVC, we use folding to achieve it, but the definition of IVC is a cryptographic primitive for proving the correctness of an iterated and incremental computation. Now remember that incremented and incremental computations are what we wanted for this model of possibly infinite running program. So what programming model best enables this kind of system? Well, actually, coroutines give us this. So the definition of a coroutine is a system that allows execution to be suspended and resumed, which generalizes functions for cooperative multitasking. And this idea of executing, suspending, and then resuming after is kind of exactly what we want to be able to define folding points, right? So you want to run until some yield point occurs. At that point, you are ending that program for this step, and then you go to some other program. This allows cooperative multitasking for especially financial applications where you need to communicate between many different systems to achieve some kind of end result. So if you think about it, program history is a series of partial computations. So even in your operating system itself, you're running Zoom right now or your browser for YouTube. Your computer is not dedicating the entire CPU to that program solely. It executes part of that program, pauses, yields to another program that runs, pauses, yields to another program that pauses and runs. But of course, this is transparent to you. Your programming language does not necessarily show you this functionality, even though it's an operating system level concern. But this concept of coroutines allows you to have this cooperative multitasking where you're specifically yielding back up to the host. And instead of this kind of operating system model where each sliver is kind of oftentimes a small predefined chunk, you can keep running that computation until you explicitly decide to yield. So if you think about it, like operating systems kind of have this like fixed step size heuristic approach, whereas we want through coroutines to have, instead of this, have the ability for programs to run until they decide to yield. And notably, this ends up being easily modeled by the UTXO system for blockchain smart contracts. So UTXOs, if you don't know, is a specific smart contract programming paradigm where you represent computations as a enshrined object that people can then resume later on. And so these have historically been used in a lot of different blockchains. For example, Bitcoin is the largest, most popular one that uses the UTXO model. But there have been a lot of other blockchains that have used UTXOs as well. And so it turns out that this coroutine system with Starstream allows you to easily represent these partial computations and this IVC, this incremental verifiable computation, this proof in UTXO blockchains as well. So Starstream gives us not only a way to have developers easily model the fold step in which states they want to intermediate proof as the intermediate state, but also allows that state to easily be compatible with blockchain systems. Now, this talk is not about Starstream specifically. If you want to learn more about Starstream, we have some videos online we've done in the past that go into a deeper dive on this technology. But we do have the ability for you to take part in these projects if you are interested. So we have a Starstream working group if you're interested in that language specifically. We also have a Midnight Discord where we're going to have some working groups there in the near future about some of this Midnight OS concepts we talked about at the start of this presentation. So hopefully that kind of gives you a good idea of Nightstream, what we're trying to accomplish, the key technologies we are using to accomplish, and of course, how you can get involved as well. So I know I've introduced quite a lot of different terms and technologies, and for each of them, I did not go in that much detail because there's a lot to cover. So I'm happy now to take any questions and kind of dig more into details if anybody's interested in some of these in more detail. I'm not sure for the host, if you want me to just read out questions as I see them, or if you wanted to read them out.
Yeah, you can go ahead and read them out as you're seeing them.
Okay. So first question is by Lucas. WRPC seems to be a concept pretty similar to gRPC, right? Yeah, that's the general idea. Basically, maybe to go back a few slides so people have some idea on this. Okay. So the idea of WRPC is to say, well, for these Wasm components, you already need to define a typed program boundary between the guest and the host. So instead of having to use something like gRPC, where you have to define a protobuf schema, we already have a schema, whiich is WebAssembly. in a sense. So the width defines the type interface, and then WebAssembly components themselves define the actual values. So I somewhat glossed over this, but WebAssembly components do not introduce just this type system, but they also introduce a canonical ABI for encoding a lot of different value types, like objects, lists, streams, and so on. And so the idea is for the Wasm component system, we already needed a type interface plus a serialization standard. So instead of having to create protobuf bindings or bindings for different RPC languages for your applications, it'd be nice if you could just leverage this work you already have to do anyways. And so WRPC kind of achieves this goal. Are there any other questions? I am looking at the questions on Zoom. So if there's any other questions on YouTube, somebody has to put them over.
I was just checking over there. I see people watching on Zoom and LinkedIn, but no questions over there right now.
Okay, question by John. How far along are you with the project? Do you have an approximate release date? So we have the proof system already developed. So the proof system, Nightstream, you can already run it to generate proofs, to verify proofs, to fold proofs together. It can already run in the browser, and it can run riscv as one of the opcode sets. We're currently working on the Wasm opcode sets, as well as some other opcode sets as well. This is still in progress. Starstream, on the other hand, the language is still being developed. So we have some specifications you can find in the repository, in the Starstream repository. But we're still making progress in the language as well as the bindings. So if you think about it, you have the Starstream language and the proving system. You need to somehow bind these together. And this is a lot of work, but we have a lot of ongoing work to do this. So you can find progress for those repositories on GitHub. Will the protocol work in both Android and OS, which I assume you mean iOS? Yeah, so we have mobile bindings for Nightstream, the proof system, in the GitHub repository already, if you want to try running it on mobile. We have a lot more limitations on mobile because on mobile, you have much more strict memory constraints. So we are able to run the proof system there. How far we're able to push with like this Midnight OS concept, I'm not sure. So for example, I think on browsers, oftentimes you have 2 gigabytes for WebAssembly as like a working buffer before your browser starts getting angry. But I think on iOS, you maybe only have like 500 megabytes. So it's pretty tight. So we have stuff working, but we'll see how far we can push it within those limits. Imans asks, what kind of overhead are we talking about when we try and prove Wasm or riscv execution real time? It's a good question. Currently, we are running riscv on 1 GPU on a laptop by 1 kilohertz. So this is still very far off from the gigahertz that people get on a regular desktop. So there's a lot of applications where, of course, performance will be too sensitive for this to be viable. But of course, for a lot of financial systems, the computation is usually not so expensive. You're just swapping values around. So this is enough for a lot of financial use cases. As well as you might have seen in the slides, one of the reasons we're prototyping like stuff like Game Boys, of course, older hardware runs at a slower clock speed. And so it's easier to model these kinds of things. Keep in mind, though, that these proof systems get over 10 times better per year. So ZK, just a few years ago would require a massive GPU cluster to get, the performance we have today. And so we're fairly confident in the papers that are still coming out and the optimizations we still have left to do that we can have this be performant enough for quite a wide range of use cases. It'll, of course, never be as efficient as raw desktop performance, But for a lot of use cases, we think that the performance hit will be acceptable if you really need privacy and provable containers. Jenny asks, is the recording going to be shared later? The answer is yes. Vinchu asks, why Wasm components in relation to Nightstream? So it's because we wanted some containerization system that has a lot of standardization work behind it, and also does not require us to have to build a whole different proof system specifically for it. Maybe to take a step back, a lot of the ways people have tried to do this kind of containerization work in the past is to generate proofs of libc or these like much higher level standards and try and like prove the entire operating system. The problem is, as I mentioned, the overhead of this provability and this private computation is pretty high. So if you have to prove an entire Linux container just to prove the state of a single application running on it, the overhead is way too high. So the benefit of Wasm components is that not only are they a well-known standard, as I mentioned earlier, they even run as OCI standard. So you can actually submit your Wasm components to Docker Hub and these other things, and they're interoperable. So not only is there a lot of standardization work behind it, they are provable with Wasm with not that much extra work. So we don't need to encode a whole new different system. And they run at a much smaller overhead because instead of having to prove the entire Linux VM, we can just prove the Wasm execution relevant for that specific application. It has this added benefit as well that we can offboard stuff into the host as required. So in this concept, you might not really have seen this, but we have marks on the top right of the application, which is like a midnight logo mark. The idea is basically some people might want to run unproven applications inside the host, or they might want to run applications that are not private. So you might say, okay, for this specific application, I'm willing to pay the performance overhead of the proof system, but for some other app that needs to run the container just because for compatibility reasons, maybe I don't care about proving other container, and then the fact that we're just using Wasm components as opposed to an ad hoc thing means that we can allow people to have like proven and unproven systems all running inside the same containerization framework instead of having to build ad hoc bindings. Ivan asks, when do you expect some text showing up in practice integrated with the Midnight network? That's obviously hard to know. Now, as I mentioned, we have the proof system working. So the proof system itself is looking very good. The other remaining work, I'm trying to figure out which slide I have this on. Yeah. The other thing is that to have this running within a ledger context, we probably don't just want, riscv and WebAssembly, but we want other opcode sets like, the EVM opcodes or different opcode sets, either for zk specific blockchains like Midnight, which is compact, and Minokawa. And so we have to actually build the bindings, the lookup tables for those opcode sets. But it's not just a question of the engineering work to build these lookup tables, which does exist. It's also about correctness, right? We need to make sure that the implementation does not have any bugs. And the difficulty of this is very large inside a financial system like a blockchain, because obviously the tolerance for any error is very low. And so right now we're working on some different attempts with Lean and formula verification tricks to try and get as much correctness guarantees we can out of these tables. One of the benefits of these lookup table systems that I didn't really touch on is actually they're much easier to prove than previous ad hoc systems. So if you think about what people were doing in the past, which was manually writing these circuits for each different opcodes that they want to support, it means they also need to somehow encode a proof system for all these different circuits. Whereas for us, we have much easier time proving correctness of tables. And so this approach not only helps us with performance, not only helps us with this kind of generalization, but actually helped us a lot with provable correctness and verification as well. All right, those are all the questions on Zoom. If there are any other questions on YouTube that I'm missing, let me know.
Let me double check one more time. I don't see, people are watching, but I don't see any questions on LinkedIn or YouTube.
All right. If no other questions come in last second, just as a reminder, you can get involved. All the code is open source, so you can go on GitHub and find all our stuff. You are more than welcome to come into our working groups. You can ping me personally and ask any questions you want. I'm happy to answer there. If you want to contribute code as well, happy to help you on board. If you want to leverage this technology for your project, your company, definitely don't hesitate to reach out as well.
Great. Thank you, everyone. And again, we'll be sending the links around. I'll send a link to the recording, slides, GitHub repos, etc. So thank you, everyone. And if you're interested in what you just heard about, join the community. Everything is open source. You're welcome to get involved, and we look forward to seeing you in the community. And thank you, Sebastian.
Thank you.
All right, bye, everyone.